This already sorted, 3, 5, 6. So it brings the 1, again, it moves the 1, 3, 5, 1, 6. It doesn't swap. Then again, 1 versus 5, 3, 1, 5, 6. And again, and I get 1, 3, 5, 6. In general, what happens at step k plus 1, at the next step? Just a general view of this insertion step. What happened at step k plus 1 is that these elements, the first k elements, are already sorted, right? The principle of insertion sort is that the first k elements are now already sorted from previous steps. All I have to do now is to figure out the next element, which is it's brought from upstairs, ak plus 1, let's call it x. This guy, we need to insert this. So the question is, where is this one goes? It's going to go somewhere among the ones that are already sorted, right? How do we do this? We swap it repetitively until it's in that spot, right? So by repeated swaps. This is already sorted. I don't have to worry about these elements. I just need to bring little by little that ak plus 1 is corresponds. We did this discussion about list versus array, how in an array, finding the spot will be only logarithmic time, because I can do binary search, right, to find exactly where it belongs. Problem is, an array is what? Even if I find the correct spot, then I have to move half of the array. What about in a list? In a list, I could insert it immediately, anywhere I want. The problem in a list is I can't do binary search to find that spot. So in a list, finding the spot takes linear time. In an array, the actual dragging or swapping takes linear time. It'd be nice to be able to do both operations in logarithmic time. The finding the spot and the putting it there, because that will minimize the whole runtime of insertion sort. List and array, they all do one logarithmic time or constant time, and the other one is linear. Therefore, this operation will be easy. So, just part of the recap. In a general, if I do analysis here, in the worst case, what's the worst case? In an array, I have to drag this how many times? Swap it with this, swap it with that, swap it with that, swap it with that. How many swaps I'm going to do? So this is number of swaps here at step k. How many swaps am I going to do in the worst case for this next element? Again, what I'm doing, I have this new value, and I'm trying to figure out where it belongs. In the worst case, what's the maximum number of swaps I have to do? K swaps, right? Because I have to swap it with every single one of them. You see here, this one had to be dragged all the way to the front of the array. So I had to swap it with all the previous 3 elements. So worst case is K swaps. How about best case? Best case is no swap at all. But how many comparisons? Let's not do swaps, let's do comparisons. In the best case, I'm going to compare AK plus 1 with AK and decide I don't have to swap nothing. Right? So that would be this next step in here. If I dig down this 8 at the next step, 1, 3, 5, 6, 8, I'll just compare 8 with 6, and I decided that's already in the proper spot. So what's the best case number of comparisons? 1. And what is the average case? That's what where is he? Right there, all the way in the back. We kind of butchered this last time, right? Like you were saying, Virgil, you kind of not very mathematical in here. Kind of cheating a little bit. Because I said, well, it's the best case, worst case K, best case 1. So okay, about half, right? About half. Let's say about half. But average case means how many swaps I do on average. I'd say K by 2. And he was pointing out, hey, we need a proof in here, right? To be exact. All right? How many people buy this so far? Hands up. Are we buying how insertion sort works? Well, in here, let's maybe not a full proof, but kind of a proof. Okay, so what's the expected number of comparisons or swaps? Comparisons will be swaps plus one, right? Because for every comparison, I do a swap until there is one comparison that is necessary. It doesn't need any swaps, so that's one more. Number of swaps, I think, is the same as the expected number of elements in set. I ignore the fact that these are sorted. In this set, A1, A2, up to AK, is the number of elements that are bigger than my value X. Right? Because I'm gonna have to swap it with every single one that's bigger than it. I know they sorted. Nevertheless, if 5 of them are bigger, it has to be swapped 5 times. If 7 of them are bigger, it has to be swapped 7 times, right? That's how this procedure works. So this comes down to, remember that number of things. Every time I see expected number of things, I do what? I break that into a bunch of binary random variables. Say Z1 plus Z2 plus ZK, where every Zi in here is what? If one is one, if AI is bigger than X, needs to be swapped, and 0 if not. Right? Every variable will be 1 for each one of these values, bigger or smaller. Everything that's bigger needs to be swapped. That's the same kind of exercise we've been seeing with expected number of things. Is the same one you're going to get tomorrow in the quiz, right? Expected number of things. You need a variable per thing that you count. Okay? We know the expectation breaks up. Not just that. It's all the same expected value. This is a sum over all k's of expected value of Zk, Zi, say. And then there's k of them, so it's k times expected value of one of them, because all have the same expectation, right? What's the expectation that one of the elements, anyone, say A1 or A3 or A5, it's bigger than X? 1/2. Because those are completely random values. When you pick an X at random, you compare with some AI at random, chances are 50-50, one is bigger, one is smaller. Okay? Of course, there are dependencies in here if you think conceptual in probabilities, but nevertheless, expectation distributes over the sum, even if they are dependent variables, so that doesn't matter. Right, so now are we happy all the way in the back? Is that more like, okay, maybe it's not fully, completely formal, but better. All right, so that's insertion sort. Insertion sort fundamental for sorting processes. Average case, as you can see here, in terms of data, is the same. In terms of the asymptotic notation, k and k by 2 are linear. Of course, this is only one step, right? I'll have to multiply with how many things I'm inserting, and I'm going to get n squared in both the worst case and the average case. Same thing happened with bubble sort. Number of bubbles or swaps, it's n squared in the worst case, but half of n squared or so, which is the same asymptotic quadratic one. Now, let's also do a little bit on this binary search tree that we talked about. That was the last thing we did. I want to build the tree with this array here. Remember how we did it? We start with the root, that's the 6, and then we say 5 goes where? Left, right? Here's a 5, and then 3 goes where? Left, left, twice, right? And then 1 goes left, left, left. Here's 1. I'm following this order, 6, 5, 3, 1. 8 goes where? Right. Then 7 goes right, left. Here's 7. Then I have 2, 6, 5, 3, left. Right? The 2 goes on the left. And then right. Here's a 2. And then I have a 4, 6, 5. Go down, left or right? Left here, 4. Okay? say I want to add an element, say I want to add the element 12 in here. Where would I put the 12? Insert 12. 12 goes in here, right? Everybody can see that. Now what I wanted to recap these three, of course. And I want to do two things, which we don't prove yet. But I know you guys are slowly feeling the pressure of these honest problems soon. So then I want to give you something to think about. One is, how do I manage to implement these three? There are two mechanisms that are very straightforward, but it's completely up to you. However you implement the tree, if it works, it's fine. You can come up with a crazy idea, that's fine. Here's one way to implement with pointers. That is, I'm creating an object, node, and inside that object, I have value and dot value. That will be for this node to be 8. I have the parent. So the parent for this would be this node right here. I have the left child for the 8, that would be this node. Not the 7, 7 is the value, but the actual memory address where this is stored. And I have dot right. People familiar with Java or C would find this perhaps the easiest implementation. I can also build it a different way to do it with a bunch of arrays. So I need to store, I'm going to have a bunch of indexes. So I'm going to throw some indexes at random, but indexes should not be at random. Let's just say we're going to index this. This is 1, this in here is 2, this is 3, 4, 5, 6, 7, 8, 9. But again, maybe some other indexes would make better sense. Let's just say I'm throwing them at random. So I have 1, 2, 3, 4, 5, 6, 7, 8, 9. I need an array here of values. That will be one array. So who's the value in node 1? 6. Node 2? 5. Node 3? 4? 5? 6? 7? 1. 8, 4, and 9, 2. Right? So I got the values array. Now I got the parents, or parent. Who's the parent of 1? Null. Let's say NA in computer science means null. When you write the program, you probably would say null, but conceptually speaking, you say NA, doesn't apply. Right? Who's the parent of 2? 6. 1. Right? So we need to keep track of indexes in here. The values are only in this values array, right? So this is 1. Who's the parent of 3? 1. Parent of 4? 3. Parent of 5? Parent of 6? Node 6, not value 6. 2. Parent of 7? 6. Parent of 8? Parent of 9? I need another array with left children. So who's the left of 1? 2. Who's the left of 2? 6. The left of 6? 7. Who's the left of 7? Nothing. Right? Left of 7. There's nothing here. Huh? Sorry. I was here. Right? So at 4, who's the left of 4? Nothing. You're right. Left of 5? Left of 6? Left of 3 is 5. Left of 6 is 7. Left of 8 is nothing. Left of 9 is nothing. And then the right array. Who's the right of 1? That's 3. Who's the right of 2? Nothing. Who's the right of 3? That's 4. Who's the right of 4? Nothing. Who's the right of 5? Nothing. Right of 6? 8. Right of 7? 9. Right of 8? Nothing. Right of 9. Okay. So now the question you have to answer, if you implement it that way, is can I do everything with those 4 arrays? Like I think of it as a tree, but I don't have a physical tree. This procedure here, if I use pointers, actually, if you look in memory, it looks like a tree, right? If that points to that, different parts of memory. These are just 4 arrays and nothing else. How do you insert a value? You know, you think of the insertion in a tree, how would I have to change all 4 arrays to produce, you know, suppose I want to insert 7.5, that goes in here, right? How do I insert the 7.5? I have to modify this array. How do I delete, say, this 8? Again, I have to modify those 4 arrays. I would say this is easier, but either way, it will take just a little bit of clearing up, and then implementation is only takes a few lines of code. But you can come up with a different strategy if you want to store the 3D. So you have to, by the time you're done with this problem, kind of work out some strategy to implement it. Now, the other thing about binary search tree is a theorem that we're going to have to do. The proof we won't do today. What is the height of the tree? So height of this tree. Height means number of layers, starting with root being layer 0. So this is layer 0 here. This is layer 1. This is layer 2, layer 3, layer 4. So the height here is 4. Starting the root at 0, how many down layers I have? That's the definition. What do you think is the worst? So for n elements, worst height is the maximum height. In the worst case, what is the maximum height with n elements? If I insert 100 elements, how down can I get? 100, right? Because 0 is the root, or 99. You're right. So that's n minus 1. What is the best? Minimum height. It's about log base 2 of n. And what is the average? By average, I mean over all arrays of size n. If I do binary search trees for every single array of size n. So I pick n equal 1,000,000, and I run many times binary search trees for that input array. Of course, it depends on the order, right? Or how these numbers are sorted. Some of them will be almost sorted out, be exactly sorted out, be pure numbers. On average, what's the height? Do you think? Of course, in the best case, is log base 2 of n, because that's we're gonna try to prove that that's easy. But on average, sometimes will be really bad because it'll be all in one branch or just 2 branches that are long. Sometimes will be nice. On average, anybody wants to take a guess? Over all possible inputs, if I make a binary search tree out of all array of size n, what do you think the average height is going to be? Yes? Nobody wants to make a guess? Well, why do you think the binary search trees are so good? Yes?
Is it still going to be log base 2?
That's why they're so good. Because the average is still logarithmic. It is true, sometimes they go bad, they go all one branch, and then they're effectively a list, but on average, they're very good. So that's a difficult theorem, I would say master level theorem. But since we're doing this expected value of insertion sort per bucket, that's pretty close to the same thing. Okay, so now that we've done this, that's my recap for sorting and with the honest problem.
Yes.
Let's move into what we need to do today. What was here? Sequences plus series and induction. So let's worry a little bit about series and sequences. I have to tell you from the beginning, this is nothing new. It's just a lot of recap. You're going to be like, I've seen this, but I don't remember it. right? So I need to go home and see how that works. And not a big deal. So what are the sequences that we need to worry about? Of course, there's many more sequences than those, but here's how the linear ones looks like. They govern by the rule xk is some a, b, c are fixed coefficients in here, a times k plus b. So let me do some examples here. K equal 1, k equal 2, k equal 3, k equal 4, k equal 5, k equal 6. So let me see. I'm gonna try to an example. Let's say A is 2 and B is 5. Don't laugh at me. I know this is like 5th grade, okay? But we have to do it anyway, just in case, because it's in the homework. So if A is equal to B equal 5, for K1, what do I get?
7.
Good. And then?
9.
9, because that's 2 times 2 plus A and B are fixed in here. It's whatever I choose. So then I go, the next one will be 11, 13, 15, 17, right? We should also do, that's important to remember. I know it's easy if I say, but what is the step? Sometimes it's called delta, like from xk plus 1 minus xk, meaning how much the increase was. With every time I move to the next element, how much was the increase? In general, that's A, easy to see. AK plus 1 plus B minus AK plus B. B goes away with B. AK plus 1 minus AK, that's just 1A. And in here, the delta was 2. You can clearly see the next guy will be 19, the next guy 21, and so on and so forth. And this is a general rule. Let's do another example. How about, so that's kind of one example. How about A equal minus 6 and B equal 1? What would be K equal 1? The same rule applies, but I have different controllers A and B. So minus 6 times 1 plus 1 is how much? Minus 6 times K equal 1 plus B, which is 1. What's the next one? Now let's see. Minus 6 times K equal 2 plus 1. Negative 11. What's the next one? What's the next one? Next one. Of course, the delta, the progression here, how much the difference is between the next element and the current element is, of course, A, which is minus 6. And that's easy to see. Every difference here is minus 6. It's a constant difference. In fact, that's the easiest way to recognize an arithmetic progression or sequence. When you see constant differences, right, you know it's arithmetic. So let me write that down. Delta is constant. Easy to recognize as arithmetic. Okay? Do we need more examples here? A equal 3, B equal minus 10. What's the first one? Come on, guys.
Negative 7.
Next one.
Minus 4.
Next one. Minus 1, 2, 5, 8. Right? Delta is 3, of course. Okay. That's it. That's arithmetic series. Let's also do, since what I did, let's do the that's arithmetic sequence or progression. Let's do the series, arithmetic series. Series means for every sequence, it's the sum of the first n terms. K equal 1 to n of xk. How do I sum up the first n terms? So that's going to be, of course, the sum of, who is this k? AK plus b, right? And now I can break these sums. I can get the a common factor, k equal 1 to n of k, plus how many b's are here total? Plus b, plus b, plus b. How many b's are there? N b's? That's outside the sum. So did we compute before this guy? We did, right? 3 times already by accident. How much is 1 plus 2 plus 3 plus 4 plus that sum for k equal 1 to n of k is plus n, right? I know last time someone was saying summed up the 1 plus the n, remember? And then sum up the 2 with n minus 1. You guys remember that trick? 1 plus n, how much is that? N plus 1. 2 plus n minus 1? N plus 1. 3 plus n minus 2? There's an n minus 2 here. That's one way to do it. The other way, maybe easier, is to write this backwards. N plus n minus 1. It's the same idea. Plus 3 plus 2 plus 1. Sum it up. 1 orange plus another orange is 2 oranges. N plus 1 is n plus 1, n plus 1, n plus 1. Just how many times I've got n plus 1 in here? How many n plus 1s? Is it clear where n plus 1 comes from? 1 plus 1, n plus 1. 2 plus n minus 1, n plus 1. N minus 2 plus 3, n plus 1, so on and so forth, right? How many of those n plus 1s are there? N. So 2s, it's n times n plus 1. Therefore, how much is s? We did that one. We'll do it again, but here's another way to show it. So now I have this sum computed. Let's plug it in. What do I get? A times n plus 1 by 2 plus nb. So I have a series that says if you have an arithmetic sequence and you sum the first k terms, this is what you get. Of course, it depends of the controllers, A and B. You can see different sequences correspond to different controllers. And the end, if you sum up the first 10 items, is different than if you sum up the first 20 or the first 30 or the first 50. As an exercise, let's do a mental thing. What happens if I want to sum up not the first n, but from 100 to 200 of some sequence? Suppose I want to know, I know how to do the first n, but the problem is not asking for the first n. It's asking from 100 to 200. Say starting at 100. Can I write this in a way that allows me to compute it as a function of the first few? How?
You do it as the first 200 minus the first 100.
Right, so from 1 to 200 of xk minus, let's be careful here, this k should go from where to where? So I got the first 200, I need to start at 100, so which one should I take out the first one, 1, 2, 3, up to which is the last one I need to take out to be left with 100 in here? So it's a general trick. If you know how to do the first n for any n, you could do the first, any chunk. Has to be a contiguous chunk from like 100 to 200, because you do all 200 that you know how to do, minus the prefix that you need to take out. That works for any sequence of any kind. It's kind of trick. All right, so that's arithmetic. Let's do another one, quadratic. Well, the xk here is ak squared plus bk plus c. Our friend from homework, what was it? 5, right? Let's solve a quadratic equation there at some point. All right. Well, let's do the same, right? So I have here some examples. Say k equal 1, k equal 2, k equal 3, k equal 4, k equal 5, k equal 6. Here's an example. Let's start with a equal 1, b equals 0, c equals 0. What do I get? AK squared plus BK plus C. A, B, C are the controllers here. They fix coefficients. What do I get for K equal 1? A times K squared plus B times K plus C. I get 1 squared. How much I get for 2? 2 squared, 3 squared, 4 squared, 5 squared, 6 squared. Okay. What's the step in here? Let me ask that a little bit later. Let's do another one. How about A equal minus 1, B equal 2, and C equal 1? I don't know if you guys minus 1 times 1 squared plus 2 times 1 plus C. How much is that? I told you it's like 5th or 6th grade, but you'd be surprised how many people made mistakes on the 6th grade. 2? Okay. How about for K equal 2? That's minus 1 times 2 squared plus B2 times 2 plus C, 1. How much you get? 1. Oh, what about the next one? That's minus 1 times, how much is K squared? 9 plus 2 times K, that's 2 times 3 plus 1. So how much is it? Negative 2. What's the next one? We have to go quick. Very good. Next one. Next one. Is that true? So how much is minus 1 times 6 squared? Minus 36. 2 times 6 is 12. Minus 36 plus 12? Negative 24 plus 1? Negative 24. All right. And let's do another one. A equal 2, B equal 0, C equal minus 2. What's for K equal 1? It's 1 squared times 2. B doesn't matter, it's 0. Minus 2, which is the 0. Next value. That's 3 squared times 2.
16.
Yeah, next. 30. 48. 70. Let's check this 48. 5 squared is how much?
25 times 2.
Times 2, that's 50. Minus 2 times 5 is? That's just minus 2. 0 times 5 is 0. So it's 50 minus 2, 48. One more. Minus 3, B equals 7, C minus 1. What's the first value? 1 squared times minus 3 plus 7 times 1 minus 1. 3. Next value. Two squared times minus 3 plus 2 times 7 minus 1. It's trial and error. Again, 2 squared times minus 3 is how much? Minus 12 plus 7.
4 plus 14. So 14. 7 times 2.
7 times 2, 14. 3 times, it's minus 12, 14. Minus 1. How much? Next one. That's going to happen in the exams. I mean, the homeworks, you can drag it out, waste 10 hours instead of 5. But in the exam, you got to be able to do these calculations. Okay? They're all very simple. Arithmetics, multiplication, additions. But you have to do it. Minus 3 times 3 squared plus 7 times 3 minus 1. How much is it? I got you 7. Next one. Minus 21. Minus 41. Minus 67. What's the step in here? Xk plus 1 minus xk. If I do a times k plus 1 squared plus b times k plus 1. B times k plus 1 plus c minus ak squared minus bk minus c. Right? I wanna, let's do how much we get there. C minus c goes away. bk plus 1 minus bk. AK squared minus AK squared goes away. What else I have here? I have a 2AK, and I also have a times 1 squared, which is how much? A. So the delta is 2AK plus A plus B. Let's verify that. So how much that delta should be, say, between those two guys in here?
Are you using the second k value or the first k value calculating the step?
The delta is xk plus 1 minus xk. So in this case, k is 3, k plus 1 is 4. Right? So this should be delta for k equal 3, because it's from k plus 1, 4, minus the 3. So that should be, according to our formula, 2ak plus a plus b, which is 2. How much is a? Minus 3. K is, in here, 3. Plus a, minus 3. Plus b, 7. How much is this? 2 times minus 3 times 3 is minus 18. Minus 3, minus 21, plus 7, minus 14. Is that the correct delta from here to here? So this step is like, what's the quadratic step? Now this step, can I point out that this is a linear? This was a constant. That's how I recognize an arithmetic series. I see constant difference. Minus, 3, 3, 3, 3, so on and so forth. That's an arithmetic series. How do I recognize a quadratic series? The deltas have to be an arithmetic progression. Like if you look at the delta, what is this delta here? Minus 2. What is the delta here? What is the delta here? Minus 14. What's the delta here? What's the delta here? Minus 26. Is this here an arithmetic progression? Minus 2, minus a, minus 14, minus 20, minus 26? What's the step of it, of this one? Delta of the delta. This is minus 6. I look at the differences. They form an arithmetic progression. You can see clearly it has a step, a constant step. That's why the original one was quadratic. For people who know calculus, this is an obvious statement. When you differentiate a quadratic function, what do you get? A linear function. How much is ak squared? What's the differential of ak squared plus bk plus c with respect to k? Plus b, right? It's not exactly the step. What's the differential of AK plus B? So, for people who know calculus, without going into proof that way, that's why the steps of arithmetic is constant and of quadratic is arithmetic, because the differentials work that way. Okay, what about the partial sum here? If I want to do the partial sum, the series, which is the sum, like before, k equal 1 to n of xk, that is the sum from k equal 1 to n of ak squared plus bk plus c, which is, I have to break this into sum of k equal 1 to n of k squared plus b sum k equal 1 to n of k plus c. Right? I break the sum into three sums. A goes in front of the first sum. B goes in the front of the second sum. I make a mistake here. It's c times, how many c's are here? N c's. Now this is again our friend, which we know how to compute, right? Because we already done it the fourth time on the board there. But how about this guy? Do you guys know how to compute this? So here's another one. S quadratic S2 of n is 1 squared plus 2 squared plus 3 squared plus n squared, written nicely from k equal 1 to n, sum of k squares. Anybody knows how to do this? Because this one we did those tricks with add the last one plus the first one, see what you get, right? Nice. How about it here? Can I add the first one with the last one? The same trick, and then the second with the next to last? Would that work? No. Anyway, we don't know what this dude is yet. That's fine. A times that dude, S2 of n, plus B times S1 of n, which we know already. That's S1 right here. Plus Cn. At some point, we have to compute this thing to figure out how to calculate this. I mean, I know the answer, but so that's an easier question, right? There's two questions here. One is, if you don't know the answer, can you figure it out? That's a hard question. The easier question is, if I tell you the answer, can you prove it's correct? Suppose I tell you the answer. N times n plus 1 to n plus 1 by 6. That's the one. Now, if I show you that answer, can you prove that it's always that? Somehow. So that's a definitely easier question, knowing the answer, just trying to show it, versus not knowing the answer. You have to do both, find the answer and show it. So if we replace that in there, for the sake of calculation, what am I going to get? A times n plus 1 times 2n plus 1 divided by 6. That's the sum of squares. Plus b times n plus 1 divided by 2. That's the sum of linear sums. Plus Cn. Okay? But we haven't proved that one yet. All right. That's the quadratic series. So it has three controllers. It's a sequence. I can add up the partial sums. The deltas are arithmetic. That's perhaps the easiest way to recognize it. When somebody show you a series or a sequence, you should do a bunch of deltas to just get the the idea of what's about. The other series that we have to deal with is geometric. Xk is A times R, okay? For some reason we don't use B. I mean, we can do B, but most people use R in here for the base. So just to not get you confused, most of these geometric series use R. But that's just a notation. You could put B in here and have the base of the series B. So A and R are constants. So let's see how that works. Again, we have k equals 0, k equals 1. We'll start at 0 this one. We can start at 1, and we can start those at 0, right, if we want to. If I do k equals 0 here, what do I get for x0? If I put 0 in this equation, what do I get? C. So that would be 0, and here x0 would be how much? 1. I can do k equals 0 here too, right? If I do k equals 0, how much is x0? B, so that's 5, right? I prefer starting at 1, but you can start at 0. In fact, we can start at -3 if we want to. Same thing, it will work. This geometric series, it's easier to start at 1. So let's do 1 here, I equal 1, I equal 2. K equal 2, K equal 3. Let's save this for later. K equal 4, K equal 5. What happens with this sequence if A is 1 and R is 2? That'll be the powers of 2, right? 2 to the 0, 2 to the 1, 2 to the 2, 2 to the 3, 2 to the 4, 2 to the 5. What happens if A is -1 and R is 1/4? How much do I get? This is what? -1. This is 1/4. This is -1/16. -1. Because every time the A is -1 stays a -1, R is 1/4. So for K equal 1 is going to be 1/4. For K equal 2 is going to be 1/4 squared. -1/4 cube, -1/4 to the 4th, fifth, so on and so forth. Here's another example. A equal 3, R equal -1/2. What do I get for K equals 0? If I put 0, R at 0 is 1. So I just A is 3. What's the next value? So it's 3 times -1/2 at power 1. What's the next value? 3 times -1/2 at power 2. How much?
3 or 4.
What's the next one? Good. Now, what's the delta here? The delta here, we also call it a step, but it's not the difference. The difference is not interesting. In these problems, we measure delta, how much is from here to here as an amount. Here we measure delta as a ratio, xk plus 1 divided by xk. So that is A rk plus 1 divided by A rk. How much is the ratio? R. So you see all this, if you look at the k plus 1 versus k, if you do the ratio, you always get -1/2. In here, you always get 1/4. In here, you always get 2. The ratio between the next guy and the current guy is always this R. That's why it's geometry. So what about the sum, the series? That is the sum from k equals 0 to, say, n of xk. That is the sum from k equals 0 to n of a times r to the k, right? So a is a common factor. I would like to write this so you can see it without the sum symbol. What's the first term in here? R to the 0, right? Plus what's the next term? R to the 1. What's the next term? R to the 2. What's the last term? A is already in front of the sum. So this is R at 0, R at 1, R at 2, up to R at n, R to the n. We did this. I think we hit it with the coupons at some point, and we had to show what it is. So we involve a trick. Anybody remembers the trick? Right, so we say geometric was what? R to the 0 plus R to the 1 plus R to the 2 plus R to the n. And what did we do? Say R times G will be R1 plus R2 plus R3 plus R at n plus 1. Now subtract Rg minus G. Of course, R1 with R1, R2 with R2, everything goes away. I'm left with R at n plus 1 minus R at 0, right? So in here I do G common factor. G times R minus 1 is R n plus 1 minus 1. So then G is R at n plus 1 minus 1 divided by n minus 1. That's what we did when we needed this, I don't know, last week or a week before. So we have that proof there. This is going to be A times R at n plus 1 minus 1 divided at n minus 1. This whole trick works only if R is not 1. So I can't divide with 0, right? I can divide with anything but 0. Negative, that's fine, but not 0. So that's what happened here. I can do it for, this is if R is not 1. But what if R is 1? Can I do this just manually? If I put R equal 1 in here, how much is this series? R to the 0 plus R to the 1 plus R to the n is how much? How many 1, 1, 1, 1, 1 are here? N plus 1, because it's from 0 to n. So in the special case, R equal 1, we have to do it manually. That's it. Sequences in series. How long did it take? Half an hour, as promised? Right? Of course, there's a lot of calculation going around. There is one thing that you have to know, the idea, the plan. Again, it's just calculations. If I give you the series, the sequence, say I give you this one, minus 5, minus 11, minus 17, and I'm not going to tell you what it is. I'm going to ask you, what kind is it? You're going to say what? Arithmetic, because it has a fixed delta. But then I'm going to ask you, can you give me back the A and B, the controllers? How would you, so this is a typical problem. Given the sequence xk is minus 5, minus 11, I'm thinking the second one, minus 17, minus 23, minus 29, and minus 35. What kind? The answer is arithmetic. And then what is A and B? How do I find the A and B for this sequence? Yes?
A is the step of the sequence, and you can use, you know that K equals, it starts at K equals 1.
Right. Assuming it starts with K equal 1, K equal 2, and this is K equal 6.
And then you know A and K and find B.
That's true. I would like a more systematic approach that works on all sequences, arithmetic or not. Kind of like set up some equations and get A and B out. Can I say A times 1 plus B has to be who? For K equal 1, A times K equal 1 plus B has to be minus 5. And for K equal 2, I get A times 2 plus B equal minus 11. Can I get A and B from here? It's a system of two equations with two unknowns. I can solve it. Can I get K equal 3 also? A times plus B equal. Do I need a third equation? No. But I could obtain those equations, right? So generally, when you get a sequence or a function in a continuous domain, and you know the type of the function, so you know it's Gaussian, you know it's linear, you know it's quadratic, you know it's a polynomial, you know it's exponential. This is called fitting the parameters. I know what kind it is. I know some values of the function. And I know it's a linear function. So I have to now fit to find the parameters A and B of the function. Can I do the same thing in here? If somebody gives me this thing, saying here, how do I find A, B, and C. If somebody tells me this sequence. First, I have to figure out what kind it is, right? What's the kind? I look at 2 to 1. That is what delta? Minus 1, right? 1 to minus 2. Minus 3. Minus 2 to minus 7. So what do I get for the delta? Minus 1, minus 3, minus 5, minus 7, and minus 9. Minus 1, minus 3, minus 5, minus 7, minus 9. Looks like it's linear. So my guess for the original sequence is quadratic. So now how do I set up the equations to solve them to get the controllers, the parameters A, B, C? A times 1 squared plus B times 1 plus C is how much? The first one, 2. The second equation, A times 2 squared, K squared, plus B times 2 plus C is the second one. That's got to be 1. This one here. And the third equation for K equal 3, so this is K equal 1 here, this is K equal 2, this is K equal 3. A times 3 squared plus B times 3 plus C has to be who? Minus 2. Now, those looks like they have squares in them, but are those equations quadratic or linear? In ABC. Remember, I have to solve for ABC. This is a 2 squared, but it's just a 4. This is a 3 squared, it's just a 9. The actual equation in ABC, is that a linear equation? So it's 3 linear equations with 3 unknowns, and I solve it for ABC, just like you did with the Markov chains. I think the calculations, you can get stuck or not, because everybody can make mistakes, but you have to understand the procedure. Somebody gives me a sequence, I guess it's quadratic or linear somehow, and then I plug in the ABC and see if it works out. Once I found ABC, it's easy to check if those are correct or not, because I can do the next few values. I got 2, 1, and minus 2. Those are in here. I get K equal 4 now. Check if I have minus 7, K equal 5, K equal 6. That's why I can verify that my ABC generates the whole this whole sequence. And another type of problem that you will be asked to, what is the next value here? If I give you this sequence, you have to guess first it's quadratic. What is the next value? There are many ways to do that. One way is to say, I solve for ABC. Now I have the controllers ABC. What value of K do I need to plug in there to get this value? This will be the next K. So this is K equals 7, right? So if I plug in 7 times minus 1, 7 squared times minus 1, plus 7 times 2 plus 1, I should get the next value. Another way of getting is to figure out what the next delta must be. If this is a linear deltas, minus 1, minus 3, minus 5, minus 7, minus 9, what's the next delta? Negative 11, so negative 11 should give me 34. That's how I get the next value. But the systematic approach is to find the parameters, ABC. Once you have the ABC, you can do everything. Compute the next value, compute the partial sum, everything you want. Okay. So, since I'm at it, before I discuss induction, I want to put something on the board that's, we're not going to deal with it right now, but just so you know. There is another kind of series called harmonic, and that is as a sequence, it's 1 over 1, 1 over 2, 1 over 3, you know, so on and so forth, 1 over 4. The general form is 1 over k. As a series is the sum of, so this is xk. Sum from k equal 1 to n of xk. That's the partial sum of the first 10 elements. It's the sum from k equal 1 to n of 1 over k. So that is 1 plus 1, 2, plus 1 over 3, plus 1 over 4, plus 1 over 3, so on and so forth. Plus the last one, 1 over n. And this series, it's called h of n harmonic even numbers. So the sum of the first n inverted values, natural numbers, is the harmonic number. I think some of you know an approximation maybe of this. This is roughly what? Anybody have seen this before? This is very close to what?
Log n.
Which log?
Natural.
Natural log. So log base e of n, right? That sometimes people call ln of n. That's a log base e. E is about 2.71 something, right? So the natural log is not exactly equal to that. Is very, very close. Now, we don't know this approximation until we prove it, so you can't use it in a homework or so without proof. But we'll end up proving it possibly Friday. I want to point out that this is a harmonic series. And the homework question has something similar. There's a homework question in there that has a h2 of n, which is 1 over 1 plus 1 over 2 squared plus 1 over 3 squared plus 1 over 4 squared plus 1 over n squared. So that's not the harmonic series, obviously. It's related to it. And, you know, what is this? That's a good question. No, right? That's for the, like, you know, master students say. But definitely mathematics can answer those questions. You just need to know more math to figure out how much this is in closed form. That's series and sums. We'll do more exercises with this once we do induction. So about induction, how many people have seen or done induction? Hands up. Some people. We're not going to assume that you guys know anything about induction. So because of that, I'm going to start with a story, right? Which is the how to think of an inductive statement. Let's do it on that side here. Instead of statement, we're gonna move from statement to be clear that we mean an implication. Back to week number 3, logic. An inductive statement is an implication. And sometimes in proof of inductions, how do we call this particular implication? We call it the inductive step. So what do I mean? If today sun goes up, tomorrow the sun will go up. That's an inductive statement. If today the sun goes up, then this then is the implication. Tomorrow the sun will be up. If my parents are rich, I will be rich. That's how capitalism works, more or less. I don't know. Is there an implication somewhere in here? Because I don't see a then. The statement in common English refers to an implication statement. I mean, this comma here, is that effectively an implying thing? If that, then that is a premise, conclusion sort of thing? What's the premise in here? Parents are rich. What's the conclusion? I'm rich. Okay. If a house is flooded, the house next to it is flooded. Here's another example. If one's Facebook account is hacked, then his or hers friend's Facebook account is hacked. All of these are implications. And what makes them inductive implications is that they kind of implies one another, right? If today the sun goes up, then tomorrow will be up. But this statement applies for tomorrow too. If tomorrow the sun is up, the next day will be up. And then the same statement applies for the next day. If 3 days from now the sun is up, so would 4 days from now the sun will be up. This statement refers to any day. How about this? If my parents are rich, I will be rich. How about my kids? If I'm rich, my kids will be rich, because it's the same statement. Instead of applying it to my parents and me, I apply it to me and my parents. How about my grandkids? If my kids are rich, their kids, that is my grandkids, will be rich, so on and so forth. So my whole family will be rich, right? This is for any parents or kids. How about this one? If a house is flooded, the next house is flooded. But now if I apply the inductive statement, the implication here for that next house, what do I get? If this house is flooded, then the next house is flooded. And if this one's flooded, then this one's flooded. And since this one's flooded, I apply the induction statement again. The next one is flooded, so on and so forth. All the houses on the street are flooded. Because these inductive statements, once you get a conclusion, you can apply that statement again with the conclusion as premise, and you get a new conclusion. If my Facebook account is hacked and he's my friend, then his is hacked. But now he's his friend, applying again the induction implication. His account is hacked, and then his friends are hacked, and then their friends are hacked, and so on and so forth. All the graph with the friends in Facebook are hacked accounts. Do you see how this works? It's not just a simple implication. It's an implication that can be applied at repetitive times. So, what is the statement? The statement in here, P, it's going to be applied for a day. At day P at day K is the sun is up at day K. And the implication what's the implication? If the sun is up in day K, then how do I write that? Sun is up in day K plus 1. P of K plus 1. How about in here? I'm going to say the statement is a generation of K, so the same, PK is generation K is rich. That's my parents, K equals 7. My parents are the 7th generation in this family, right? So what is the implication? It's the same, right? If my parents are rich, the next generation, that means their kids, they are rich. What's the statement in here? If a house is flooded, the next house is flooded. House at number K is flooded. So the statement is the same. If this house number K on the street is flooded, at the next number, it's also flooded. And what is the chain implication? P of 1 implies who? P of 2. P of 2 is a logic statement that says the sun is up in day 7. That's the statement. And P of the sun is up in day 1, therefore the sun is up in day 2. Therefore, from P of 2 I can get P of 3. From P of 3 I can get P of 4. and so on and so forth. I think from here I can get all of them. That means the sun will always be up. How about the last one? What's the statement? Person K account is hacked. So one person is hacked, next person is hacked, the other person is hacked, so on. I think it's very important to, when somebody shows you a problem, if you think about induction, to figure out first what is the exact statement at a particular instance of day, person, generation, whatever the instance is there. I think it's extremely useful to write this statement down like this. Doesn't have to be in English, could be in math. But that's the statement P of K. Now, about these implications, can I conclude that if this happens for every K, all the implications are true? If P of 1 implies P of 2, and P of 2 implies P of 3, P of 3 implies P of 4, there's a chain of implications that are happening here? But can I conclude the statements of them, of K, all of them, are them true? So, if the sun is up today, then it's going to be up tomorrow. If it's up tomorrow, then it's going to be up the day after, and so on and so forth. Did I say anywhere in here that the sun is actually up? Remember, premise implies conclusion, right? The implication can be true. Can I have both the premise and conclusion being false? Even though the implication is true? I can. So by saying this implies that, implies that, implies that, doesn't make them true, even though the implication is true. I need another thing to make all of them true. If this house is flooded, then that house is flooded. If this house is flooded, then the next house is flooded. If this is flooded, so on and so forth. Doesn't mean the houses are flooded. No. I was talking in the case of a flood. But it doesn't mean right now the house was flooded. What else do I need to make the case that all the houses are flooded? Which premise? Just one, right? If I can prove P of 1, so again, that implication chain, let me write it down again. Chain. P of 1 implies P of 2, implies P of 3, implies P of 4, so on and so forth, implies P of K, implies P of K plus 1. And it doesn't stop. It keeps going. Now, this could be all true, but all of them could be false, right? Because implication works on false implies false. To conclude that all of them are true, what do I need to prove here again? I need to prove this one's true, right? So what's called a base case is proof P of 1 is true. Because now if this is true, the only way all these implications are true if every single one of them is true. Because true all implies true, and true implies true, implies true, implies true, all of them will be true. So in the case of houses, if one house gets flooded, all the houses after that have to be flooded if the implications are true. Same thing with the parents being rich. That may be true, right? If a family is rich, their kids tend to be rich. But it doesn't mean everybody's rich. You gotta have richness at some point to start from there where it's true. Then the kids, the grandkids, the great-grandkids, so on and so forth, etc., right? So in an induction proof, we have to clarify who's P of K and what is this implication or step. As a requirement, you have to write down the step before you argue anything. You have to say from where I go to where. And then we need two proofs. We need the implication proof that this is true. That makes the chain. And then we need the base case. Most books and treatments, and even this class, use the base case first. I think it's much better to do the base case last. Because if you do it first, you don't know where the base case starts. But if you do it last, it's going to be obvious. So if you do the induction proof first, the actual step, it's going to become very clear what base case you need. So my recommendation for you, it won't matter for the grade where you put it, but it'd be to do clearly state the step. who's pk and who's the implication. Then do the induction proof from here I get here. And then establish, okay, what's the best case? Where do I need to start the base? Here. Prove that case manually. Let's look at some examples. I would like to do this one first. So, let's get, I don't know, did we? Okay. So I want to prove Sn is 1 plus 2 plus 3 plus n. Prove that this is n times n plus 1 divided by 2. I want to prove this by induction. Now my statement P of n is exactly that. Sn is n times n plus 1 by 2. That is my statement. What is the induction step? Induction step is P of n implies Pn plus 1, right? I use n instead of k, but I can use any letter I want. So I have to write this down. Please write this explicitly down. It's good for the grade in case you mess up the proof, but also good for you to clarify what is it that you're proving. So before we're proving, I'm going to state explicitly the induction step. So what does this mean? If the sum for, this is sum from k equal 1 to n of k, right? If the sum from k equal 1 to n of k is n times n plus 1 by 2, then this is the induction step. This is the implication. From Pn, I go to Pn plus 1. What is this statement for n plus 1? The sum for k equal 1 to what? n plus 1 of k, right, has to be what? It's not n times n plus 1 by 2 anymore. It's this function, but with n replaced with n plus 1, right? So how much I get? n plus 1 times n plus 2 by 2. I didn't prove anything yet. I'm just stated what the induction step. If this is true for a particular n, like 75, then it's going to be true for 76. That's what I wrote here. I didn't actually prove that. That's not a proof. I'm just stating what the induction step is. Instead of writing 75 to 76, I wrote it in general for any n. This states from 75 is true for 76, but also for 13 implies the 14, and for 25 implies the 26. For any value you put there, you're saying if was true for the previous n, then it's true for this n. Hands up with me. This is an absolute Achilles heel in mathematics, understanding induction step. Unfortunately, like everything else, when somebody said it nicely, it makes total sense. And when you go home, here's an induction homework. Okay, what's the induction step? Damn. Right? I wish sometimes I go back at my lecture, and sometimes I wish I wouldn't say it so nicely, so that people don't assume it's, oh, okay, piece of cake. Like, oh, of course, that's the induction step, right? It's not, of course. You have to write it down, and sometimes the implication is difficult. Most mistakes in induction come from getting this wrong. Right here. It's k has to go to n plus 1. This is n plus 1 times n plus 2, but some people would write it still as n times n plus 1 by 2. Some people write something else. Most mistakes come from not writing correctly the induction step. Now for the proof, we always start with the conclusion, with some guy in here. We say, how is it the sum from k equal n to n plus 1? That's what I want, as n plus 1. In induction, in the proof, we try to relate to what we have. In this proof, can we use this? If I want to prove that, can I use this fact? I can. Does it mean it's true? No. It means I can use it. If this is false, any implication will be true from false. All I have to show if this is true, then that's true. So then I can use this, it's called induction hypothesis. So naturally the proof will have to use that fact somehow. So we have to relate what we have here, this dude, with this dude. What's the relationship between them? Common sense English, not mathematically. What's up with this sum versus this sum? Yes?
The conclusion is the terms plus and plus one.
It's the same sum with one additional term. That's what it is. So I can write this is the previous sum from k equal 1 to n of k plus an additional term, that's n plus 1, right? Now I use the induction hypothesis. Induction hypothesis tells me something about this, right? It tells me what this is. So what is it? N times n plus 1 by 2 plus, I have to still add n plus 1, that comes from here. And now let's add up those two guys. This is n plus 1 common factor times n by 2 plus this is a 2, right? Plus 1 plus 1. So that is n plus 1 times n plus 2 divided by 2. Is that right? Because this 1 is 2 by 2, so it's n plus 2 divided by 2. Is that done? Am I done now? Did I get n plus 1 times n plus 2 by 2? Now, when you do an induction step, you should specify for what n this is true. This is an implication. I'm going to say for every n starting with at least 1. Maybe it's not true for minus 1, I don't know. I'm just proving it starting at 1. Everybody followed my proof here? What did I do? I started with the one I needed. And the first thing, before writing anything down, I was like, how can I relate this with the previous one that I had? The relation is the same sum plus an additional thing. So I write it as the one I know plus the additional thing. I replace this one with what I know it is. This comes from the induction hypothesis. Then n plus 1, I do some arithmetics here to figure this out. I get what I want. Now what I prove is effectively P1 implies P2 implies all of them P of 100 and keep going. If I look at my chain of implications here, which one do I need to be true to be done with this? Because remember, the chain of implications doesn't guarantee they're all true until you have a base case. So what's my base case? Looking at this chain, the base case is n equal 1. So let's prove it for 1. S, this is S of n. S of 1 is 1, which is supposed to be 1 times 1 plus 1 divided by 2, right? Is that true? So I just replace in the formula, if I have just 1, this is 1 times 1 plus 1 divided by 2, true or false? That's done. So I proved this now the 5th time by induction, because it has a base case, and I prove all the implications. The induction step has to be general. It can't be from P of 2, you get to P of 3, because we need all the implications. It has to be for n goes to n plus 1, so I get the whole chain at once. If I prove from 3 I go to 4, then I have to prove from 4 to 5, then I have to prove from 5 to 6, so on and so forth. Yes?
Or we have to write some sort of,
What?
or the whole, we have to write some sort of.
Right. Therefore, P of n is true for all the n's. Right. So P of n true for all n. I started at 1. Yes.
So I mean, in that case, it's pretty obvious what your inductive step is. But what's like the intuition or the technique?
We always try to relate the what we want with the induction hypothesis. So that's always the case. Now the intuition, it depends. If there's a hexagon with corners and triangles, cut a triangle becomes a pentagon. So I related the pentagon or hexagon this way, right? If it's a bunch of dots on a circle, that's in the homework. Well, if I can prove this for 100 dots, can I prove for 101 dots? So take a dot out, see what happens to the remaining 100 dots, apply the, like you always have to relate what you want with what you know how to do, which is the induction hypothesis. Let's, where is that, this one? Can we prove this one by induction? Yes.
All n greater than or equal to 9. Is that
The implications.
Is that what integers?
Right. I mean integers. All those P of, she's right. In here, all those P of n's, I mean n is a natural number. So it has to be an index. From 1 goes to 2, from 2 to 3. There are possibilities to do it with not integers, but you have to control the index. It has to be enumerable. So it doesn't work with real numbers. Do you think we can prove this one here? This one, yes.
This question from before, are you always adding integers? Or is it?
Depends what index I use. I may prove from I minus 1 to I. That's still, it has to be clear from where to where the induction step, the implication goes. But sometimes I may go from P of I minus 2 to P of I plus 1. That's a different kind of induction. That jumps every 3 steps if I need to. Nevertheless, it provides a chain, right? This one will be from 1, I get to where? If this is 1, what is this? If I minus 2 is 1, how much is I plus 1? And from 4 goes to where? And from 7 goes to where? See? If I prove this induction step, I will have some implications, but not all the p's in there. Sometimes you're going to see at recurrences, something like that. How about if I prove from P of n by 2 implies P of n? That means from P of 1 I go where? From P of 2 I go where? Right? So there is some chain of implications, but not all p's or all indexes are there. We're going to have to deal with those cases Friday and the week after that. So there's all kinds of inductions that do not jump from one to the next one necessarily. But the basic version is this one. So what is my statement here? My statement is P of n is S2 of n, the sum of squares, k equal 1 to n of k squared, is indeed n times n plus 1 to n plus 1 divided by 6. So what is the induction step? Again, please write it down before you prove it. If the sum of k to n of k squared is n times n plus 1 to n plus 1 divided by 6, then what? This one is the basic one where I go from n to n plus 1. How does this look for n plus 1? K equal 1 to n plus 1 of k squared is what? N plus 1 times
N plus 2.
2n plus 2 plus 1, right? Divide by 6. I'm not sure if I do this because somebody showed me a draft of the next homework and I think it's in there. Maybe I don't want to do, but is it in there? I don't know. Did we publish the next homework? Maybe not. How would I do this if I am to prove it? I will look at this one, right? Start from here, and I say, what's the relationship between this sum and this sum? Same question like before. What is that relation? How do I look at this sum versus this one? Because this is the induction hypothesis, and this is the induction conclusion. If I want to deal with this sum of squares, what's the relationship between this and the previous ones?
The larger one is equal to the smaller one plus n plus 1 squared.
Right. So that's how I have to start. This k plus a equal 1 to n plus 1 of k squared is the previous sum, k equal 1 to n of k squared, plus the last term. And now I can replace, given the induction hypothesis, I can replace this with this equation. Hopefully, instead of this, I'm going to put this, and hopefully I'll get that with some arithmetic manipulations in there. I'll let you do that and fill up the base case. Let me show you another one. So that we're going to prove this one, which is this. By the way, you have to know this answer because it's going to come up in the quadratic series. And if you don't know this answer, your exam or homework or quiz will be much harder. You have to know this, like the sum of linear sum 1 plus 2 plus 3 plus n, the quadratic sum 1 squared plus 2 squared plus 3 squared plus n, and the geometric sum. You have to know this by heart. So how about the geometric one? Sum from k equals 0 to n of, what did we say? R to the k. We say that's r to the n plus 1 minus 1 divided by r minus 1, right? That's the geometric series, and that's what we computed. We did it already. We proved it with some jumbled up. Write it again by r, do the subtraction, see what happens. Okay, but how about by induction? If this is my statement, P of n, what is my induction step here? I'm going to write the induction step. The sum from k equals 0 to n of what? R to the k. It's n plus 1 now. Has to be who? How do I write this? Not on n, but on n plus 1. What would this be? R is fixed here. R is a constant.
Be r to the k plus 1.
No, it's still r to the k. It just goes one more term.
On the right side of the equal.
Here?
No, I see.
This is still r to the 0. So this in here is r to the 0 plus r to the 1 plus what's the last term? R to the n. This one here is r to the 0 plus r to the 1 plus r to the 2 plus what's the last term? R to the n plus 1.
I was looking in the wrong place. I was looking in the wrong place.
So what do I put instead of this? What would this be for my induction conclusion step in there? N plus 2 minus 1 divided by n minus 1. Let's prove this induction step. Again, what's the relationship between this sum that I need and the one that I have already? The sum from k equals 0 to n plus 1 of r to the k is the previous sum plus the extra term. Which one is the extra term? What term is in here that was not in here? Because the previous n plus 1 terms are all here, but there's one more dude in here. Right? R at n plus 1. Now this one I know how much it is from the induction hypothesis. So I'm going to replace that with, that's what I use the induction hypothesis. That's R at n plus 1 minus 1, right? Divide by r minus 1. I replace it with this in here. Plus r at n plus 1. So now if I do the arithmetics for the fractions, that is r at n plus 1 minus 1. how much I get here? R times R at n plus 1. It's R at n plus 2, right? And minus 1 times this guy is minus R at n plus 1. Again, I have to multiply this R here with R minus 1 to bring it as a common denominator, right? R times R at n plus 1 is R at n plus 2. And minus 1 times R at n plus 1 is minus R at n plus 1. Now this guy goes away with this guy. And what am I left at the numerator? N plus 2 minus 1 divided by minus 1. Right? Because that's what I wanted, right here. Hands up, who's with me? I know you are with me, but you need to practice it. See how quickly this thing goes here? And I'm gonna go that quickly for the first time. But once you do a little practice, it's gonna go quick. I need a base case. You have to add the base case in. Let me show you one more, and then I'll let you go. Sum of first and odd numbers. Is n squared. What this is saying, what is the sum of the first odd numbers? It's from k equal 1 to n. What are the odd numbers? 2k minus 1, right? What's the first odd number? First odd number. Is that in here? 2k equal 1, I get 1? Or the second odd number? 3. This has to be n squared. Now that's my P of n. So the induction step is what? The sum from k equal 1 to n plus 1 odd numbers of 2k minus 1 has to be not n squared anymore, but instead n plus 1 squared. How do I prove this thing? I start in here. Sums are the easiest because the new sum is the previous sum plus a thing. Other things are not so easy, but sums are always the easiest. This sum from k equal 1 to n plus 1 of 2k minus 1 is the previous sum, k equal 1 to n of 2k minus 1, plus what's the last term, the extra term in this sum? Exactly. It's 2 times n plus 1 minus 1. That is the new term. Right? So now I use the induction hypothesis. This I already have. It's n squared. N squared, right? Plus, how much is in here? 2n plus 1, right? Because it's 2n plus 2 minus 1. It's 2n plus 1. How much is n squared plus 2n plus 1? Done, because that's what I want, n plus 1 squared. We need a base case. Please add the base case. N equal 1. So next time, we'll do more induction proofs. More
I'm also going to pull head here just to make sure. Like, I'm not going to take any. Yeah, we don't know this. My cycle. Yeah, right there. 19.4? Yeah. And it's like illegal NUPD, 9th floor interrogation room right now. Two-way mirror.
Let's go Gabe, Loves, Dash, Daddy's, Dash.
is the third 2k minus 1.
Dude, when does camera get here? When the camera gets here? Before disco.
Yeah, for you guys, we'll be all the data. I think there is the two good questions that could be answered.